Exercise 1710 is asking you just to predict the products for this electrophilic addition to conjugated dienes. So it's similar to the previous exercise, but where we'll still have the 1,2 and the 1,4 product, but here we don't have to draw the whole mechanism. And there is one other addition to this. In addition to drawing the products, we have to say which one predominates. Is the 1,2 product the major product, or is the 1,4 product the major product? So to understand that, let's think about just 1,3-butadiene and how, without drawing the mechanism, we could quickly predict the product for that. So let's say we have 1,3-butadiene, and we're adding that, adding HCl to that. Well, there are two products we can get. We can get the 1,2 product, or we could get the 1,4 product. So you could number that conjugated system, and we can number each of the carbons in our product. And you would add, for the 1,2 product, you'd add the hydrogen to carbon number 1 and the halogen to carbon number 2, in which case the pi bond between 3 and 4 stays the same. Or you could add the hydrogen to carbon number 1, the chlorine to carbon, or the halogen to carbon number 4, and in order for that to happen, resonance has to rearrange that pi bond to go between carbons 2 and 3. So you get the 1,2 product and the 1,4 product, as we've seen a bunch in the previous exercise. Just watch out about how that pi bond changes in the 1,4 product. You'll have it always, in the 1,4 product, the pi bond will always be between carbon 2 and 3. So you get each of these, the 1,2 and the 1,4 product, as the major product under different conditions. When the hydrogen and the chlorine first add to the molecule, so you have the hydrogen and the chlorine, and the hydrogen adds on there, so the pi bond goes away and turns into a sigma bond to the hydrogen. When that happens, you create a carbocation right next door, and you have that full negative charge on the chlorine. So the chlorine is really close to a positive charge. Now at low temperatures, movement becomes difficult, and the chlorine has a hard time diffusing to other parts of the molecule. And so at low temperatures, the chlorine will kind of be stuck in this one place, and it'll just end up sticking to that positive charge, in which case you'd get the 1,2 product. So the 1,2 product is the major product at low temperatures. And low temperatures, that'd be something like 0 degrees Celsius. However, if you raise the temperature, then diffusion is no longer a problem. The chlorine can attack anywhere. And as we saw, we have two resonance structures in the mechanism for this. And the other resonance structure is the one that has the carbocation at the 4th position. So you have the pi bond here. Now, if diffusion is not a problem, then the chlorine can get over there and attach there to carbon number 4, and so you get the 1,4 product. So that's if diffusion is not a problem, it could attack anywhere. And the place where it'll attack at higher temperatures, when diffusion is not a problem, is to give you the 1,4 product, because that gives you the more stable alkene. So first let's write this down, and then we'll explain why. The 1,4 product is the major product at high temperatures. And for example, that would be something like 40 degrees Celsius. So at high temperatures, diffusion is not an issue. So the major product you'll get will just be the one that is the most stable, because you could form anything. So what we will do is consider the different types of pi bonds that you can have. We're going to end up getting the most stable product at high temperatures, so we have to think about what that is. The most stable product has the most carbons bonded to the double bond. So double bonds are classified by how many carbons are bonded to them. If one carbon is coming off of the carbons in the double bond, then it's called mono-substituted. If two carbons are coming off of the carbons in the double bond, and it doesn't matter which two carbons, it's called di-substituted. If three carbons are coming off, it's called tri-substituted. And if four carbons are coming off of the carbons in the double bond, it's tetra-substituted. Now, if you think about the bonds that are here, in that where you have the double bond, you have pi bonds there. You have you have a pi bond there. That means you have two parallel p orbitals. Now, if you're going to form a sigma bond to a hydrogen, the orbital of the hydrogen is a small, tiny little s orbital. So if you had a hydrogen there, you have that tiny little s orbital. And that s orbital doesn't overlap very well with these p orbitals. If you have a carbon, so instead of a hydrogen, if you have a bond to a carbon has an sp3 hybridization. So you'll have an sp3 orbital going down and to the left, an sp3 orbital going down and to the right, but the third sp3 orbital will be going up and at a diagonal. And that third sp3 orbital lobe lines up with the top of the p orbital. And that allows the electron density in these p orbitals to bleed a little bit into that one sp3 orbital. And the fact that two parallel p orbitals can bleed a little bit into one of the sp3 orbitals of a neighboring carbon is called hyperconjugation. And the big principle in organic chemistry is that when you spread charge out, it becomes more stable. So the more of these carbons that you have bonded to the double bond, the more sp3 orbitals there are next door that the electrons in this pi bond can sort of bleed into. And so they stabilize themselves in that way. So the tetrasubstituted pi bond is the most stable type of pi bond, double bond that you can have, and a monosubstituted would be the least, at least in this series, the least stable type of pi bond that you can have. So if we go back to our two products, notice the 1,2 product left us with an alkene that was only bonded to one carbon. There was only one carbon attached to the double bond, so that's monosubstituted. Whereas the 1,4 product left us with the carbons in the double bond bonded to two carbons. It's disubstituted. And so the 1,4 product is the more stable product. And so at high temperature, where diffusion is not an issue, where the chlorine can move around, it can move to the other side of the molecule and attack either of the positions, it's going to attack the position that gives you the more stable product more often. And so at high temperatures, the major product is the 1,4 product. So that's all you need to remember for this. You need to be able to draw the 1,2 product and the 1,4 product. You'll always get both of them. And then you just need to remember that the 1,2 product is the major product at low temperatures, and the 1,4 product is the major product at high temperatures. So that's what we're going to do in each of these cases here. So first, we don't have to draw the mechanisms here. We're just drawing the products. So we'll redraw the molecule. And I'm going to count. So I'm going to draw this molecule twice because we're going to get two products. The 1,2 product and the 1,4 product. And I'm going to number this so that it's easier for me to draw those two. So these are our two products now. We're adding HBr. So we're going to add an H and a Br. On the first one, I'm going to add the H always at carbon number 1 and the Br at carbon number 2. So that's one of our products. The other product is if the H is attached to carbon number 1, it's always on, the hydrogen is always on carbon number 1, but the bromine is on carbon number 4. Now to do that, you have to rearrange that pi bond. The pi bond in the 1,4 product goes between carbons 2 and 3 because of the resonance that we saw in the previous exercise. So these are your two products, your 1,2 product on the left and your 1,4 product on the right. And to know which one is the major product, you look at the temperature. The temperature is 40 degrees Celsius, which is a high temperature. And because of that, the major product is the 1,4 product. And the minor product would be the 1,2 product. The major product is the 1,4 product because this double bond here has a higher substitution. It's got 1, 2, 3, 4 carbons bonded to it. It's tetra-substituted. Whereas this other one has just 1, 2, 3 carbons bonded to the double bond. It's tri-substituted. So this 1,4 product is the more stable product, and at high temperatures diffusion is not an issue, so you can form that product. You can get the bromine to diffuse fast enough to form that more stable product. So for B, we'll redraw the molecule. We will count, so we'll number these 1 to 4. And now I'm going to copy and paste this. We want 2 copies of this because we're going to get the 1,2 product and the 1,4 product. We're adding H and Cl. For the 1,2 product, hydrogen always goes on carbon number 1, and the chlorine will go on carbon number 2. For the 1,4 product, hydrogen always goes on carbon number 1, and the chlorine will go on carbon number 4. The pi bond, remember to shift that, change it so that it goes between carbons 2 and 3. So those are your two products, the 1,2 product on the left, the 1,4 product on the right. Here the temperature is very low, so diffusion is difficult. The chlorine has a hard time getting all the way to the 4th carbon, and so it just attacks the positive charge that develops next to where the hydrogen was added. And your major product at a low temperature is the 1,2 product, and the minor product would be the 1,4 product. You'd still get both. It's just the 1,2 product would be the major one. Finally, for C, we've got this molecule here. Let's just redraw that. And we can number this. Number that conjugated pi system, 1 to 4. And I'm going to duplicate this because we're always going to get 2 products, the 1,2 product and the 1,4 product. And so we can draw those in. Now we're adding H and Br. H will always go at carbon number 1. So we get rid of that pi bond, H goes there, and in the 1,2 product, the bromine will go on carbon number 2, and you're done. For the 1,4 product, H always goes at carbon number 1. To make room, we'll get rid of that pi bond. And then for the 1,4 product, the bromine will go on carbon number 4. Don't forget to add in the pi bond between carbons 2 and 3. So those are your 2 products there. Then we just have to say which one is the major product and which one's the minor product. At 0 degrees Celsius, diffusion is hard to do. The bromine has a hard time moving around, getting around the solution, getting to the carbon number 4. So it just sticks to the carbocation that develops at carbon number 2, and the 1,2 product is the major product. So at a low temperature, like 0 degrees Celsius, the 1,2 product is the major product, and the 1,4 product is the minor product. So in this exercise, we've seen how you can just predict the two products of an electrophilic addition reaction to conjugated dienes without having to draw the mechanism, and how you can use the temperature to predict which of those two products is the major product. At low temperature, the 1,2 product is the major product because diffusion is difficult, and at high temperature, the 1,4 product is the major product because that's the one that's technically more stable because it always has the higher substituted alkene.